we are going to study about 2 degrees of freedom systems. So, in the previous classes you have studied about the free and force vibration of single degree of freedom systems. In case of free vibration of single degree of freedom system, you have studied the system without damping and with damping. In case of system with damping, you have studied 3 different cases. One is under damped case, second one is the critically damped case, and third one is the over damped case. In case of steady state response of the system, so you have determined the steady state response using different methods. So, you have used a simple force polygon method to derive the magnification factor, or you have derived the steady state response of the system. So, the total response of the system you know equal to the transient response of the system and the steady state response of the system, and in case of a system with damping, so that transient response die down and you have only the steady state response. So, in case of single degree of freedom systems, you have studied also about the rotating unbalance, support motion, wheeling of shaft and different vibration measuring instruments. So, today class we are going to study about 2 degree of freedom systems. So, you know that many machine components cannot be modeled as a single degree of freedom system. So, it may be modeled as a 2 degree of freedom system. For example, if you take a simple system like a double pendulum. So, I am drawing a double pendulum. So, already we have studied about the case of a single or simple pendulum. So, in case of a simple pendulum, so you have a bob, so with mass m, and it is hung by a string, massless string of length L. So, in this case you have derived the equation motion. Now, to derive the equation motion for this case, in which you have, let you have 2 mass m. So, this is m1 and m2 and they are hung by 2 springs. So, you require more number of coordinates to express the motion of this system. So, you require to define the motion of this point, and you require to define also the motion of this point. So, define the motion of these 2 points. So, you require minimum 2 coordinates to express the motion. So, these 2 coordinates may be this theta 1, theta 2. So, it may be the motion of this, so theta 1, and the motion of this also theta 2. So, you can find the motion theta 1 and theta 2. So, these are the 2 minimum coordinates you require to express this motion of this double pendulum, or you just take this another simple spring mass damper system or spring mass system. So, this is one mass and this is the other mass, they are connected by the springs. So, if you want to express the motion of these 2 mass, here the minimum coordinates you required the motion of this mass, that is x1. So, this is m1 and this is m2, and the motion of this mass, this is x2. So, here also you require the minimum coordinates 2. So, when you require 2 coordinates to express the motion of the system, then this will be a 2 degrees of freedom system. In case of a lathe machine also, you can model the lathe machine with its headstock and tailstock. So, let this part is the headstock and this part is the tailstock, and it is on the bed, and the support can be modeled as a spring. So, you can model this lathe as a 2 degrees of freedom system with this headstock mass here. So, this is m1, this is m2, and this you can concentrate or you can distribute the mass of the bed and other parts in these 2 parts. So, in this case the vibration of this you can express in different ways. So, you can write the vibration or motion of this in the transverse direction by this motion of this, let the motion of this will be x2, the motion of this may be x1. So, you can express this motion by x2 and x1, or you may express the motion by the angular displacement. So, motion, so let this is the equilibrium position, and so you can express the motion by this displacement x and this angle theta. So, in this case you can express the motion by this translation motion of this mass center by x, or and the angle theta. So, there may be different ways to express the motion of the same system. For example, in case of this double pendulum, you can express the motion by theta 1, theta 2, or you may express the motion by putting a coordinate system. So, a coordinate system you can put, this is x, this is y. So, you can write this coordinate of this in x 1 y 1. So, you can write it x 1 y 1 and the coordinate this is x 2 y 2. So, either you can express the motion of this double pendulum by using this coordinate x 1 y 1 x 2 y 2 or theta 1 theta 2. So, these coordinate x 1 y 1 x 2 y 2 are the physical coordinate of the system. So, you are describing a reference point from which you are finding this motion x 1 x y 1 and x 2 y 2. So, these are the physical coordinates of the system. So, in this case also you can have a physical coordinate, you can fix the coordinate system x and y here. So, you can, so this will be your y coordinate and this is the x coordinate you can fix. So, from this x y you can, from this coordinate system, from the equilibrium point you can take, let this is the equilibrium point position. So, you can take this as a. So, it will be a plus x 1 and similarly you can take this point. So, let this is the equilibrium position. So, from this you can take this as b. So, the physical coordinate of this you can write as a plus x 1 I for mass m 1 and for mass m 2 you can write the physical coordinate as b plus x 2 I. So, you can write, so where I and j are the unit vector in x and y direction. So, in these cases or in case of a multi-degree or 2-degree of freedom system, you can use different coordinate systems. One is your physical coordinate system and other one is the generalized coordinate system. A generalized coordinate system is a system in which you are expressing the motion of the system by using minimum number of coordinates or minimum. So, in case of this double pendulum, this theta 1 theta 2 are the generalized coordinates and x 1 x 2 x 1 y 1 x 2 y 2 are the physical coordinates of the system. So, by using these generalized coordinates or physical coordinates you can derive the equation motion. Already you know, to derive the equation motion you may use the inertia principle. So, you may use the inertia principle or you may go for this energy principle. So, today class I will tell you how to derive this equation motion by using this both inertia principle and energy principle. In case of inertia principle, you know you can use Newton's method or you may use D'Alembert principle, and in case of energy principle you can go for this Lagrange principle. You can go for Lagrange principle or you may go for extended Hamilton principle. So, in both the cases, in case of Lagrange principle or extended Hamilton principle, you require to find the energy of the system and the work done by the forces of the system. So, energy of the system include the potential energy and kinetic energy, and work done by the non-conservative force also you have to find. In case of inertia principle, so you are using Newton's second law, either you are using Newton's second law or you may go for D'Alembert principle. So, you know both the methods are similar, and you are converting a dynamic system to an equivalent static system by using the D'Alembert principle. The D'Alembert principle, if you recall, the D'Alembert principle is nothing but, so if you have a mass subjected to a force, let it is subjected to a force F, this is a mass m, so it will be accelerated by an amount a, or this acceleration you can write in terms of x double dot. So, according to this D'Alembert principle, you can convert this dynamic system to an equivalent static system by incorporating the inertia force of the system. The inertia force is nothing but mass into acceleration, and it acts in the direction opposite to the direction of acceleration. So, the inertia force direction will be this. So, the inertia force is mx double dot, and it is acting to the opposite to the direction of acceleration. So, this is the acceleration direction of acceleration, and it is acting to the opposite to the direction of acceleration. So, according to Newton's second law, so your equation motion becomes, so according to Newton's second law for this case, so if you have a mass m, it is subjected to a force F. So, already I told you that inertia force is mx double dot, and this is your acceleration x double dot. So, according to Newton's second law, your F equal to mass into acceleration, but according to this D'Alembert principle, summation of forces which include the inertia force will be equal to 0. So, F minus mx double dot will be equal to 0. So, this is D'Alembert principle, and this is Newton's second law. So, already you know, by using this Newton's principle, Newton's second law or D'Alembert principle, you can derive the equation motion of a single degree of freedom system. So, today we will derive some of the equation for the 2 degrees of freedom system by using these Newton's method. So, let us take a simple 2 degree of freedom system with 2 mass and springs. So, let me take 2 mass. So, this is mass m1. So, it is connected to another mass m2, and so they are connected to a rigid constant. So, let me write this spring constant K1. So, this spring constant K2 and this spring constant equal to K3. So, I can write the equation motion by taking a physical coordinate system here. I can take a physical coordinate system from a reference coordinate system, or I can take a generalized coordinate system. Let me take a generalized coordinate system. Let x1 and x2 are the generalized coordinate system. So, this x1 and x2 are the coordinates I have taken from this equilibrium position of mass m1 and mass m2 respectively. For a physical coordinate system, I can take, this is the reference axis. So, this is I can take x axis and this I can take y axis. So, for a physical coordinate system, I can take this x and y coordinate system, and this equilibrium position I can take this equilibrium position from this end I can take it as A, and from this I can take it as B. So, the physical coordinate, if I want to write, then this physical coordinate I can write it equal to A plus x1 and B plus x2, but by using these generalized coordinates, now I am going to derive the equation motion by using D'Alembert principle or by using Newton's second law. Both are same, already you have seen. One, in case of D'Alembert principle, you are converting that system to an equivalent static system. So, for finding this equation motion, I have to draw the free body diagram. So, already for a single degree of freedom system, you know how to draw the free body diagram. So, this is for mass m1 I can draw the free body diagram, and then for mass m2 I will draw the free body diagram, and then I will write the equation motion. So, for this mass m1, the forces acting on this mass m1 are the spring force K1 x1. So, as the mass will move towards right, then the spring will be extended, and in turn it will exert a force K1 x1 on the mass. So, it will exert a force K1 x1 on this mass K1 x1. So, the other force acting on this, so to the right of this spring K2. So, due to the motion of this mass m1, it will be compressed by an amount x1, and due to the motion of this x2, it will exert a force on this mass m2 in this direction, and so the net motion of this spring or net motion of this spring will be equal to x1 and x2 in this direction. So, as the net motion of the spring in this direction is x1 minus x2. So, the force acting on this mass will be equal to K2 into x1 minus x2. So, in addition to these two spring forces, the force acting on the mass is the inertia force also. So, this inertia force already you know that it is opposite to the direction of acceleration. So, it will have a force m1 x1 double dot. So, it is equal to m1 x1 double dot and it acts opposite to the direction of motion. Similarly, for mass m2 I can write, so I can write the equation motion for this mass m1 like this. So, summation of all the forces will be equal to 0. So, the equation motion will be equal to m1 x1 double dot plus all the forces, you just note that they are acting in the same direction. So, m1 x1 double dot plus k1 x1 plus k2 into x1 minus x2 equal to 0. Now, I will draw the free body diagram of this mass m2. So, for mass m2, what are the forces acting? Forces acting by spring k2 and spring k3. So, when this mass is moving towards right, so the spring k3 will be compressed. So, it will exert a force on the mass in opposite direction. So, that force equal to k2 k3 x2, and so this force is k3 x2, and this spring already you know that it has a relative motion of k2 x1 minus x2 in this direction. So, on this mass it will exert a force, or it will exert a force. So, if you are writing in the same direction, so it will exert a force of k2 into x1 minus x2 in this direction, or if you want to write in other way, so you can write a force of, so in this way also you can write x2 minus x1. So, either you can write k2 into x1 minus x2 opposite to this direction. So, you just see that the net force acting on the springs would be equal to 0. So, this force plus this force, they if you add it, it is equal to 0. So, either you can write it in this form k2 into x1 minus x2 in this direction, or k2 into x2 minus x1 in opposite direction. And in addition to this, you also know that the inertia force m2 x2 double dot is acting on this. So, in this case the equation motion becomes, so no other force is acting on the system. So, the equation motion becomes m2 x2 double dot plus k2 into x2 minus x1 plus k3 x2 equal to 0. So, now you have a set of equation, this is equation number 1, this is equation number 2. So, you have two equations for this system. So, these equations you can arrange in a matrix form also. So, you can write this as mass matrix into x1 double dot x1 double dot x2 double dot plus stiffness matrix into x1 x2 x1 x2 equal to 0 0. So, 0 0 because there is no force acting on the system and you are considering a free vibration of the system. So, if you want to consider the force vibration of the system, let a force, if a force F is acting here. So, if a force F is acting on mass m2, so in your second equation will be converted to m2 x2 double dot plus k2 x2 minus x1 plus k3 x3 equal to F. So, in this case your mass matrix becomes, so you just note that it is equal to m1 0, and in this case it is equal to 0 m2. So, m1 x1 double dot plus 0 m2 x2 double dot, and in this case this is k1 x1 and this is equal to k2 x2. So, k1 plus k2. So, you can write this is equal to k1 plus k2 and then minus k2. Similarly, you can see for this case it is equal to k2 x2 minus k1 x1. So, this is equal to minus k2 x1 and this is k2 x2 and this is k3 x2. So, this becomes k2 plus k3. So, your stiffness matrix becomes k1 plus k2 minus k2 plus k3 x1 x2, this is 0 0. So, if a force is acting, so this 0 will be replaced by a force F. So, in this way you can find the equation motion by using either D'Alembert principle or Newton's principle. So, already you know about the physical coordinate system, you can put a reference frame and from which you can measure the coordinates and you can write the equation either in terms of the physical coordinates or in terms of the generalized coordinates. In this case, in this example, I have taken the generalized coordinate x1 and x2 and I have drawn the free body diagram of the system. Free body diagram of mass m1 I have drawn first. So, in this case the forces are acting spring force k1 x1 and for this middle spring. So, as it is shared by these two displacement, this is in this side you have a displacement x1, in this side you have a displacement x2. So, the spring will have a net displacement of x1 and x1 minus x2 and you will have a force k2 into x1 minus x2 acting on this mass m1 in this direction and in the opposite direction it will act on mass m2. So, you can see that the net force acting on this mass m1 and m2 by the spring k2 will be equal to 0. So, in this way after drawing the free body diagram, so summation of all the forces will be equal to 0. In case of a rotating system you can take the summation of moments also equal to 0. So, by using the equilibrium principle, so you can derive the equation motion of the system. And you can see in this case the mass matrix is, so the mass matrix is m1 and 0 and 0 and m2 and in this case the stiffness matrix is k1 plus k2 minus k2 minus k2 k2 plus k3 x1. So, if you take a coordinate system in such way that the mass matrix and both the stiffness matrix will be uncoupled, then you can write the equation motion like this: m1 x1 double dot plus k1 x1 will be equal to 0 and m2 x2 double dot plus k2 x2 equal to 0. So, you may have a coordinate system, let a coordinate system q1 and q2 for which you can write the equation motion in this uncoupled form, that is you can write m1 q1 double dot plus k1 q1 equal to 0 and m2 q2 double dot plus k2 q2 equal to 0. So, in this case you can see that you can reduce this 2 degree of freedom system to an equivalent two single degree of freedom systems and already you know the solution for a single degree of freedom system. So, those coordinate system by using which you can write the equation motion in an uncoupled form are known as the principal coordinate systems. Those coordinate system by using which you can express this mass matrix and stiffness matrix in an uncoupled form is known as the principal coordinate systems. So, by this time you know three different coordinate systems. One is your principal coordinates, one is the generalized coordinate system, one is the physical coordinate system and the third one is the principal coordinate system. In case of physical coordinate system, you are describing or you are taking a reference axis and you are describing the position of the mass or the position of the points whose motion is required by these physical coordinates, and in case of a generalized coordinates you are taking a set of coordinates which are the minimum number of coordinates required to express the motion of the system, and in case of a principal coordinate system you are taking a coordinate system in such way that the mass matrix and stiffness matrix are uncoupled. A system in which the mass matrix is uncoupled, so you can write a system in which the mass matrix is uncoupled, that is in this way you can write. So, the equation will be 0 m or this way. So, in this case the mass matrix is uncoupled. So, the system in which the mass matrix is uncoupled is known as dynamically uncoupled system, or if it is coupled then this is known as dynamically coupled system. So, dynamic coupling. So, in case of dynamic coupling you will have, instead of 0 you may have some term. So, let it is m1 m2. So, this is m11 m12. So, this will be m21, this will be m22. So, already m22 we have written. So, In case of a dynamic coupling, you will have this M1, M12 and M21, and in case of a dynamically uncoupled system, you will have this M12 uncoupled. For uncoupled, you will have this M12 and M21 equal to 0. Similarly, you can have static coupling of the system. In case of a static coupling, you will have the stiffness matrix uncoupled, that is stiffness matrix you can write in this form. So, you can write K1, K11, K12, K21, K22. So, in this case if K12 and K21 are not equal to 0, the system is statically coupled, and if it is equal to 0. So, if this is equal to 0 and this term equal to 0, then this system is known as statically uncoupled system. So, for principal coordinates, so these are the coordinates of a system in which you have the mass matrix and stiffness matrix uncoupled, or in other words you have a system with both dynamic and static uncoupling terms. So, in case when you are using the principal coordinates, you can reduce it 2 degree of freedom system to equivalent single degree of freedom systems, and you can find the solution easily in that way. So, now let us see the other method to find the equation motion, that is the second method, the Lagrange principle. Using the Lagrange principle we will find the equation motion of the system. Already I told you, in case of Lagrange principle or in case of extended Hamilton principle, we can use, or you can have the potential energy and the kinetic energy of the system. Let T is the potential energy of the system and U is the kinetic, or V is the potential energy of the system. So, T is the kinetic energy of the system and V is the potential energy of the system. So, according to Lagrange principle, d by dt of del T by del q k dot minus del T by del q k equal to this capital Q k, where this capital Q k is known as the generalized force. So, this is known as the generalized force, and the small q k is the generalized coordinate, small q k is the generalized coordinates. Already you know, in case of this double pendulum, theta 1 and theta 2 are the generalized coordinates. So, in case of Lagrange principle, you are using generalized, say a set of generalized coordinates. So, in this case d by dt of del T by del q k dot. So, k is 1 for 2 degree of freedom system, this k equal to 2. So, k will be equal to 1 and 2. So, in this case you can write the generalized the equation motion using this expression, or you may write this like this. So, it will be equal to d by dt of del T by del q k dot minus del T by del q k plus del V by del q k equal to q k n c. Q k n c is the generalized force, generalized non-conservative force. So, you know this q k is the generalized force which contain both conservative force and non-conservative force. So, the first equation is applicable for all the systems, whether it is conservative or non-conservative. So, when you are separating the conservative and non-conservative forces, already you know that the non-conservative force or the work done by the non-conservative force equal to negative of the potential energy. So, by applying that principle, you can rewrite this equation in this form. So, it will be equal to d by dt of del T by del q k dot minus del T by del q k plus del V by del q k equal to q k n c. Already you know that this Lagrangian of a system in case of a single degree of freedom system was written in this form, L equal to T minus V. So, T is the kinetic energy, V the potential energy, and L is the Lagrangian of the system. So, L equal to T minus V. So, by using that, so you can write the same equation in this form, that is d by dt of del L by del q k dot minus del T by del q k equal to del, this is del L by q k, del L by del qk equal to qk nc, where L equal to T minus V. So, if you include the damping of the system, then you can write the equation motion in this form. So, d by dt of del T by del qk dot minus del T by del qk plus del d by del qk dot plus del V by del qk will be equal to qk nc. So, in this way also by including damping you can write the equation motion. So, let us use this Lagrange principle to derive the equation motion for some systems. So, for the same system what we have taken before, let me draw it again. So, in this case I have a mass m1, so it is connected another mass m2 and I have 3 springs. So, this is springs k1, this is k2 and this is k3, and so this is the constraint, and so this mass m1 will have, this is x1 and this is x2. So, this x1 and x2 are the generalized coordinates. Now, you can write the potential energy of the system and kinetic energy of the system. So, the kinetic energy of the system will be equal to T equal to kinetic energy equal to half mass m1 into velocity of this. So, m1 into velocity of this mass equal to x1 dot. So, velocity dot square. So, already you know that mass into velocity square into half is the kinetic energy of the system. So, for mass m1 the kinetic energy equal to half m1 x1 dot square. Similarly, for mass m2 the kinetic energy equal to half m2 x2 dot square. Now, the potential energy of the system is due to only the springs here. So, the potential energy associated with this will be equal to half k1 into x1 square plus, already you know that this spring will have a relative motion of x1 minus x2 or x2 minus x1. So, you can write this is equal to half k2 into x1 minus x2 whole square. You just note that this x1 minus x2 whole square equal to x2 minus x1 whole square. So, whether you are writing x1 minus x2 or x2 minus x1, it is immaterial. So, for this third spring, so you can write the potential energy equal to half k3 x2 square. So, this spring has a displacement of x1, the second spring will have a relative displacement, that is x1 minus x2, and the third spring will be displaced by x2. So, the kinetic energy of the system becomes the potential energy of the system becomes the summation of the potential energy of these 3 springs, and the kinetic energy equal to the summation of the kinetic energy of the 2 mass. So, now the Lagrangian of the system can be written as T minus V. So, L equal to T minus V. So, you can write this equal to half m1 x1 dot square plus half m2 x2 dot square minus half k1 x1 square plus half. So, I can expand these things. So, I can write k2, okay, I can write this is x1 square plus x2 square minus 2 x1 x2 plus half k3 x2 square. So, this is the expression for the Lagrangian of the system. Now, by using this Lagrange principle, so I have to find d by dt of del L by del qk dot minus del L by del qk. So, there is no damping in this system. So, I can write, and there is no force also acting on this system. So, I can write this is equal to 0. So, already you have found the expression for L, and you know your q1 equal to x1 q1. So, q1 equal to x1 and q2 equal to x2. So, first you should find del L by, so you just find del L by del x1 dot, then you just find del L by del x2 dot and del L by del x1 and del L by del x2. So, you can find the equation motion. So, now del L by del x1 dot will be equal to, so from this equation you can find So, del L by del x 1 dot will be equal to, so this is the only term associated with x 1 dot. So, it will becomes half into 2 into m 1 into x 1. So, this 2 cancel, so it will becomes m 1 x 1 dot. So, this becomes m 1 x 1 dot. So, I can write this is equal to m 1 x 1 dot. Similarly, I can write this del L by del x 2 will be equal to, so differentiation of this with respect to x 2 equal to m 2 x 2 dot. So, other terms you just see are not function of x 2 dot. So, those terms derivative will be equal to 0. So, this becomes m 2 x 2 dot. Similarly, you can write del L by del x 1. So, this will become, so from this expression, so this x 1 dot term and x 2 dot terms are independent of x 1 and x 2, these are velocity terms. So, velocity and displacements are independent function you can take, and so differentiation with respect to x 1 will give. So, this part if you differentiate with respect to x 1, so this part if you differentiate, so this becomes 2 cancel. So, this becomes k 1 into x 1, and here you just see that there are some terms with x 1. So, this becomes, so k 2 x 1 square terms you can differentiate with respect to x 1. So, 2 will cancel. So, this becomes k 2 x 1, then these terms, so 2 and 2 cancel. So, this becomes half k 2 x 1 x 2. So, differentiate with respect to x 1 will becomes k 2 x 2. So, this will becomes k 1 x 1 and plus k 2 x 1 and minus k 2 x 2. So, I can write this term as, so this becomes k 1 plus k 2, k 1 plus k 2 x 1 minus k 2 x 2. Similarly, del L by del x 2 I can find. So, this becomes, so you just check, this becomes, so from these terms you can find x 2 square. So, differentiation of this will be equal to 2 x 2. So, this is k 2 x 2, and from this it becomes k 2 minus k 2 x 1, and this will give rise to k 3 x 2. So, I can have k 2 plus k 3 x 2 minus k 2 x 1. So, this becomes k 2 plus k 3 x 2 minus k 2 x 1. So, now d by dt of del L by del x 1 dot will be equal to m 1 x 1 double dot, and similarly del L by del x 2, d by dt of del L by del x 2 dot will be equal to m 2 x 2 double dot. So, my equation motion will become, so when I am writing in terms of first equation will become, so first equation I can write for this. So, del L by del x 1 dot minus del L by del x 1 equal to 0. So, from this you know that you are getting, so from this you are getting m 1 x 1 double dot. So, this becomes m 1 x 1 double dot. So, for this minus of this, so you just check this is minus of this. So, this becomes, so before that you just check this is minus. So, you have a minus sign here. So, t minus b, so L equal to t minus b. So, when you are differentiating this, so these terms becomes negative and this becomes positive. So, this becomes negative and this becomes positive. So, you can for minus del L by del q k, so you will have minus minus plus, and so this becomes, so this becomes plus k 1 plus k 2 into x 1 minus k 2 x 2, and for the second equation you can have d by dt of del L by del x 2 dot minus del L by del x 2 equal to 0. So, for this case you can write it is equal to m 2 x 2 double dot plus, so you can check it, so plus k 2 plus k 3 x 2. So, this becomes k 2 plus k 3 x 2 and minus k 2 x 1 equal to 0. So, you can write this thing in matrix form. So, matrix form it will becomes the same equation what you have got before. So, it becomes m 1 0 0 m 2 x 1 double dot x 2 double dot minus or plus, so this becomes K1 plus K2 and this becomes minus K2 and this becomes minus K2 and this is K2 plus K3, x1 x2 equal to 0 0. In this equation, this generalized force Qk equal to Fi dot del Ri by del Qk and k equal to 1 to n. So, where Ri is the physical coordinates of the system, F is the force acting on the system. So, if you have a n number of force acting on the system, by using this formula you can find the force acting or the generalized force acting on the system for writing the equation motion. So, let a force F is acting on the second mass. So, you can write that thing. So, the physical coordinates, you can take a physical coordinates, already I told you that physical coordinate will be b plus. So, b is the distance from this. So, you can write this is b. So, the displacement will be b plus x2. So, your in this case the force will have a position vector. So, you can write that is r I will be equal to b plus x2 I. So, if I am taking that direction as x direction and I is the unit vector associated with that. So, Ri I can write equal to b plus x2 I and this force I can write equal to Fi. Fi is acting on the second mass. So, by using that thing, so I can write Qk is the fast generalized force acting on the system. So, it is equal to summation Fi dot r I. So, you just see that expression. So, you can find, so from that expression you can find it. So, this is equal to Fi or Fi into del Ri by del Qk, Fi dot del Ri by del Qk. So, from that expression you can write this is equal to Fi in dot del Ri by del Qk, del Ri by del Qk. So, F1 equal to 0. So, I equal to 1 to 2. So, you have two cases. So, I equal to 1 and 2. So, in the first case F1 equal to 0, there is no force acting at station 1 or mass 1, and your F2 equal to F, force acting on this. So, you will have, so this is equal to, so if you want to write this Q1, so Q1 will be equal to 0. So, 0 and Q2 you can find this is equal to F. So, Q2 will be equal to F1 equal to 0 into this. So, in this case you can find in this way. So, you can find this. So, this is equal to F1 dot del R1. So, R1 position vector is, so your R1 equal to A plus x1 I and your R2 equal to B plus x2 I. So, where A and B are the position from this reference frame to the equilibrium position of mass m1 and this is for mass m2. So, your F1 dot del R1, so del R1 by del x1. So, as F1 equal to 0, so this becomes, so F1 I, so this is 0. So, this part is 0 as F1 equal to 0. So, the first part will becomes 0 and the second part, or I can write it in detail. So, this becomes, so while deriving Q1, so it will be equal to F1 I dot del R1 by del x1. So, this becomes I plus F2 in I and dot del R2 by del x2. So, del x2 becomes del R2 by del Qk equal to, for k equal to 1. So, this becomes x1. So, if you differentiate this R2 with respect to x1, so this becomes 0. So, already this F1 equal to 0. So, this is 0. So, this becomes 0. Similarly, when we are finding Q2, this will be equal to F1 I dot. So, differentiate this with respect to Q2 Q2 is your x2. So, if you difference del R1 by del x2, that is equal to 0 plus F2, that is equal to Fi dot. So, if you differentiate this with respect to x2, so this becomes I only. So, this becomes Fi dot I. So, this becomes F. So, in this way you can find the generalized force acting on the system. So, by finding this generalized force acting on the system, so you can write the equation motion in this form: m1 0 0 m2 x1 double dot plus x1 double dot x2 double dot plus k1 plus k2 minus k2 minus k2, this is k2 plus k3 x1 x2 equal to 0 F. Similarly, if the force is acting on the fast mass, so you can write the equation motion, and in that case you can find the generalized force and put it at the proper place. So, now you know by using the Lagrange principle or D'Alembert principle, you can derive the equation motion of a system. Also, you may use the extended Hamilton principle to derive the equation motion of a system. So, in case of extended Hamilton principle, so you can also use this kinetic energy and potential energy of the system. In terms of kinetic energy and work done of the system, you can write the extended Hamilton principle in this form. So, where del, this is the del operator. So, you can write this del t plus del w bar dt equal to 0, where del r I at t1 equal to del r2. So, if you are taking 2 degree of freedom system, so you have 2 coordinates r1 and r2. So, del r1 t1 equal to del r2 t2 equal to 0. So, this del r1 is the virtual displacement by or virtual displacement of mass m1, and del r2 is the virtual displacement of mass m2. So, already you know from the virtual work principle that virtual displacement will be equal to 0. So, according to extended Hamilton principle, so when this virtual displacements equal to 0 at time t1 and t2, so the system will obey this principle. So, that is equal to del t plus del w bar dt equal to 0. So, this w bar as the work is a path function, that is why we have written this w bar. So, in terms of Lagrangian, you can write the same expression like this. So, already you know your Lagrangian equal to t minus v. So, you can write the same expression in this form. So, del L, so integral t1 to t2 del L plus del w bar nc dt equal to 0, and using the generalized coordinate you can write this is equal to this del qk at t1 equal to del qk at t2 equal to 0. So, using either this first expression or the second expression, you can derive the equation motion of a system. So, already you know this w, del w contains 2 terms, that is the conservative work done and non-conservative work done. So, when you are taking conservative work done, so you know that conservative work done equal to negative of the change in potential energy. So, by using that principle you can write, so you can write this del w equal to del w nc plus del w due to non-conservative force, and del w due to conservative force equal to negative of the potential energy, del potential energy. So, del t minus del v will give you del L, and this will give you del w nc. So, using either this equation or this equation, you can derive the equation motion of a system. So, for a conservative system, you can see that work done by the non-conservative force equal to 0. So, in that case it will reduce to, so it will reduce to the simple form del L dt equal to 0, where del qk t1 equal to del qk t2 equal to 0. So, this is known as the Hamilton principle of this. So, this is known as Hamilton's principle. The previous one where you are using the non-conservative force is known as extended Hamilton principle. So, the detailed derivation of this extended Hamilton principle or Lagrange principle you can find from the textbook by Meyerowitz, principle and techniques of vibration or elements of vibration. Also you can find the same thing from the other books by Thomson and Balkrishnans also. So let us take one example. So in this case I have taken a simple, so let me take a simple system. So in this system I have just taken a spring and a mass, and I have attached another mass, or I have attached a rod which is hinged at this point. So in this case, and also I have applied a force F in the horizontal direction here. So in this case you can see that this will reduce to a 2 degree of freedom system, because this mass will have a motion x1 or this mass will have a motion x, and in addition to that this rod will also oscillate during this motion. So you can express the motion of this total system by writing the displacement x of this mass m and displacement of this rod. So this displacement of this rod either you can express in terms of the motion about this point, that is using this theta, angle theta, or you can express this motion also in terms of its center of gravity CG. So the CG of this rod I can locate it here. So either you can express this motion of this rod in terms of this hinged point O, or you may express in terms of this center of gravity of this mass. So let me take a coordinate system. I can take a physical coordinate system. So this figure you may see. So in this case this is the original position and this one is the displaced position. So in this original position, let r0 is the distance from this equilibrium position from this mass, and now it has a displacement x. So this is the mass m. So I can take a coordinate system y with unit vector j in this direction, and I can take a unit vector I here, this is j and this is the displacements. So first I should write the position vector of all these points. So you know the position vector of this point equal to r0 plus, so position vector of this point will be equal to r0 plus xi. Similarly the position vector of the center of mass I can write in terms of, so this will be, so r0 plus x plus this distance. So this distance you can find. So if this length is L, so this is at a distance, let it at a distance L by 2. So it will be equal, it will be L by 2. So this is, this angle will be L by 2 sin theta, and so the I component will be equal to r0 plus x plus L by 2 sin theta I, and the vertical component I can take a vertical component positive in this direction. So it will be negative in this direction. So it will be minus L by 2 cos theta j. So the position vector of point C, so this is point C, the center of gravity of this rod. So I can write that equal to r0 plus x L by 2 sin theta I minus L by 2 cos theta j. So the velocity of this, so this is the position vector. So you can find the velocity of this. So velocity will be equal to x dot. So you just differentiate this expression and you can find the velocity as x dot plus L by 2 cos theta. So sin theta differentiation will be cos theta into theta dot. So this is ith component, and jth component will be cos differentiation will be minus. So this equal to plus minus minus plus. So L by 2 theta dot sin theta j. The kinetic energy of the system you can write. So the kinetic energy of the system will be kinetic energy of this mass and kinetic energy of this rod. So the kinetic energy, total kinetic energy will be half m x dot square, half m into differentiation of this. So this is your r1, physical coordinate r1. So differentiation of this will be equal to x dot I. So velocity square or velocity, so it will be kinetic energy will be equal to half m x dot square. Similarly, the kinetic energy of this rod will be half. So, if you are taking at this point directly, you can find the kinetic energy of the rod about this point. So, in that case it will be the inertia about this point into theta dot square, or you can write the kinetic energy about this point. So, kinetic energy about this point, when you are writing, this point has both translation and rotation. So, you have to write both translational kinetic energy and potential and rotational kinetic energy. So, this is the translational kinetic energy, that is equal to half m v c dot v c, plus rotational kinetic energy will be equal to half I c theta dot square. Already you know that this moment of inertia I c equal to, if m is the mass per length of that rod, so it will be equal to m l square by 12. So, this expression will reduce to this. So, it will be equal to half m x dot square plus half m x dot plus half theta dot cos theta square plus half theta dot sin theta square plus half m l square by 12 theta dot square. So, you can add these terms by using this cos square theta plus sin square theta equal to 1. So, it will reduce to half m plus m x dot square plus m l x dot theta dot cos theta plus 1/3 m l square theta dot square. And potential energy of the system. So, potential energy of the system is due to the spring and due to the change in position of this rod. So, due to the spring it will becomes half k, as the change in distance of the spring equal to x, or displacement of the spring is x. So, it will becomes, so half k x square, and change in position of this system if you see, so it will becomes, so this is the original position, this is the original position. Now, you draw this, and now it is the change in position. So, the change in position becomes L by, so the potential energy you can write equal to, so this becomes L by 2 into 1 minus cos theta. So, total potential energy of the system becomes half k x square plus mg L by 2 1 minus cos theta. So, by using this kinetic energy and potential energy, you can write L equal to T minus V, and now you just write this del L. So, you just use this del operator. So, for a single term I will show you how you can do. So, this, if you use the del operator, it becomes m plus m 2 into x dot into del x dot. So, 2 x dot into del x dot. So, in this way you can operate this del operator, and you can write this expression like this. So, you can find this del L. So, after finding del L, so this is the expression for del L. Now, you just use the extended Hamilton principle. So, before that, the work done by this non-conservative force will be equal to Fi dot this. So, using extended Hamilton principle, you can find the expression for this equation motion. So, this becomes the equation motion of the system. So, today class we have studied about how to determine the equation motion by using Newton's principle or D'Alembert principle, and also by using this Lagrange principle and extended Hamilton principle. Next, also we have studied about the coordinate coupling of the system. We have taken 3 different types of coordinates. One is the physical coordinate of the system, second one is the generalized coordinates, and third one is the principal coordinates of the system. So, next class we will study how to determine the free vibration of a 2 degree of freedom systems.